Is slide visible?
Yes,
Yes,
sir.
sir.
Shall we start?
Okay, sir.
Okay, sir.
Okay. Good afternoon, all. Today
Good
we
afternoon, sir.
good afternoon. In the last class, we have derived the Lagrange's equation, and today we discuss some applications of Lagrange's equation. And the most simplest application is a simple pendulum. As you know, a simple pendulum is actually a bob of mass m suspended from a rigid support by a massless and an inextensible string of length L constitutes the simple pendulum. The motion of a simple pendulum is shown here. For a simple pendulum, the constraint is the length of the rod is fixed, which is L. So only theta coordinate is required, or theta is the generalized coordinate here. Here constant equation is r minus L is 0, so it is time independent constant. Second thing is constant is written in form of f of r t equal to 0, so it is a holonomic constant. So first we calculate this Lagrangian. You know Lagrangian L is equal to T minus B, kinetic energy, and potential minus potential energy. Here kinetic energy, here we use plane polar coordinate r theta angle, r is equal to L, and theta is the angle here. Uh, so you know kinetic energy in two dimension is equal to half m x dot square plus y dot square. X is equal to r cos theta, y is equal to r sin theta. You put that, you found kinetic energy equal to half m r dot square plus r square theta dot square. Since here r is fixed equal to L, so r dot is equal to 0. And putting r is equal to L, we get half m L square theta dot square. And what about potential energy? Potential energy is actually uh, depends on the height mgh, you know, mass, and g acceleration due to gravity and height. Uh, if you compare here in coming from C to B, it covered a vertical distance AB, and in terms of this length L, you can say this is length L. So obviously OA is equal to L cos theta. So OB is L. So AB is equal to L minus L cos theta. So the vertical height is equal to L minus L cos theta, which is covered by simple pendulum from coming from C to B. So here potential energy mgh, H is actually AB, which is equal to L minus L cos theta. So Lagrangian becomes T minus B half ml square theta dot square minus mg L minus L cos theta. So you know this is the Lagrangian equation, d by dt of del L by del theta dot minus del L by del theta is equal to 0. Here theta is the only generalized coordinate. So first calculate del L by del theta from this L. Del L by del theta is equal to here mgl 0 is only plus L cos theta. You know derivative of cos theta is equal to minus sin theta, so it will minus mgl sin theta. Similar del L by del theta dot is equal to how much? If you take the derivative of this term, then only this term gives you 2 into ml square theta dot, 2 half cancel, so ml square theta dot. Putting in this Lagrange's equation, we found m derivative of ml square theta dot plus mgl sin theta is equal to 0, which ultimately gives ml square theta double dot, mean double derivative d square theta by dt square plus mgl sin theta is equal to 0. This is the equation of motion. And if you take a simple pendulum, you know angle theta is very small for a simple pendulum. So in place of sin theta, you can put theta. We know for small theta, sin theta is approaches to theta. So this equation become ml square plus theta double dot plus mgl theta is equal to 0. Or dividing mg in both the term, we found theta double dot plus g by l theta is equal to 0. This is the required equation of motion for a simple pendulum. Okay, clear? Hello.
Okay, sir.
Next example is Arthur's machine. A particular machine actually used to measure the acceleration of gravity by Arthur, developed by Arthur's. Here two unequal masses are connected through a string of length L, you can say, and string is rounded over a pulley. So here we can the two bodies. So here kinetic energy and potential energy actually depends on kinetic energy and potential of M1 and kinetic energy and potential energy of M2. If you assume the length is L, then if the pulley it has a radius of r, then it will be from this point. From this point to this point will be pi r because it will be 2 pi r. So half will be pi r. So distance, if it is x, then this distance will be L minus x minus this pi r. Okay. So here coordinate is x, here L minus x pi r. So kinetic energy will be half m1 x dot square plus half m2 this derivative square, but L dot is 0, pi r dot 0, only minus x dot, and hence square of minus x dot square is equal to x dot square. So kinetic energy will be half m1 x dot square plus m2 x dot square. And potential energy here m1 gx, m1 gx minus m1 gx, because here potential energy generally origin is over here and m1 m2 are below the origin of potential energy, so it will be negative. So minus m1 gx and here minus m2 g L minus x minus pi r. By using this you can set the Lagrangian, and from this Lagrangian you can use the Lagrange's equation to getting the equation of motion. Okay, this is the once you find the Lagrangian, then a simple derivative you can get this equation of motion. Okay. Another example is a simple harmonic oscillator. This is a very popular one. So for a simple harmonic oscillator, actually, force is proportional to displacement. And actual negative of displacement, and force is equal to minus kx. So if you calculate the potential energy from the formula, you find potential energy will be half kx square. Where kinetic energy is half mx dot square, potential is half kx square. So Lagrangian will be this. From this Lagrangian, you can take the derivative of del L by del x and del L by del x dot, and finally find the equation of motion for a simple pendulum like this equation or this equation. We say that is execute a simple harmonic motion with angular frequency root over of k by n. Okay. And another example is a LC circuit. LC circuit. L is inductor and C is
What is the
yeah.
kinetic energy, sir?
Hello?
In the simple pendulum, simple harmonic motion, what was the kinetic energy?
Half
Potential
m x
energy.
dot square, only single particle. It is executing motion in x direction. So half m x dot square. Kinetic energy is same for all things.
Okay. Understood.
For LC circuit actually inductor and capacitor is capacitor. You know, capacitor stores the energy and the actually electric energy, and similarly your inductance behaves as a storage of magnetic energy. So potential energy of the circuit actually charged because magnetic energy dynamic one, it is generated by current. Magnetic field associated current, which is dq by dt q dot. But electrostatic energy is charge dependent energy. So here q is the generalized coordinate, and potential energy is half cv square stored by the capacitor q square by 2c. And kinetic energy is half li square stored by inductance, or I is equal to dq by dt. So L q dot square. Here q charge is the generalized coordinate. So we can set the Lagrangian like this, t minus b, and ultimately calculate the equation of motion. Okay, you also found this equation where you can comparing with the general equation of a simple harmonic oscillator. You say here angular frequency will be root over of 1 by LC. Next also you can do some numerical problems. Here, One thing is kinetic energy is simple half mx dot square or two dimension y dot square, but potential energy varies. And one thing is determine whether potential energy is positive and negative point. There are few rules. The potential energy is a characteristic of the system and not any individual object. Positive gravitational potential energy means the body will do work in returning to its reference position, while negative potential energy means the work will be done on the body to bring it back to the reference point. If work is done on the body, then it will be negative. If it work is done by the body, then it will be positive. Suppose it automatically comes execute simple harmonic motion, then we call it positive energy. But if you work is done from outside to moving it to the original position, then we call all the potential energy is negative. Also, sometimes gravitational potential depends on reference position. If the system was above the reference position, then potential energy will be positive, and if it was below the reference position, the potential energy will be negative. So this is important point. Sometimes given reference position, if our point is below, it will be negative, above positive. There are some numerical problems. Suppose one problem given a particular mass m slides under the gravity without friction along the parabolic path y is equal to ax square. So path is like this. Here is going to find the Lagrangian. So how you calculate? Y is equal to x square is a two-dimensional problem. Mass is moving, so obviously there are two coordinates. Point x y. Kinetic energy half mx dot square plus y dot square, and put. Uh, okay, but here given equation y is equal to x square. So you can put in place of y dot. Y dot will be 2ax x dot. So final kinetic energy is this, and the potential energy minus mgy here. So minus mg ay x square. So in this way, set the Lagrangian and then find the equation of motion. Okay. Another problem is Lagrangian is given. Lagrangian particle is given. Find the coordinate of the particle x. How you get this? You first write the equation of motion from this Lagrangian. Using this Lagrange equation of motion, you got this equation in x double dot and take double derivative. So this double derivative, so take double integration. So first integrating it, you get minus bm by d plus c1. Again integrating it, you get the x. According to question. Here, two kind of questions are asked. Either you set Lagrangian equation of motion or Lagrangian given, you find the x. Are you clear? Or any problem?
Yeah.
Am I audible?
Yes, sir.
Okay.
Yes, sir.
Okay. The next problem of a particle of unit mass moves in the plane, so that is x dot is yt and y dot is minus xt. If it is a conservative force field, then find the potential energy. Because only for conservative force field we apply the Lagrange equation in this form: d by dt of del L by del x dot minus del L by del x 0. All that. So here x dot is yt, y dot minus xt. Find the potential energy. How you get? So from this you can set the Lagrange equation. Since x dot is yt, what is x double dot? Actually, equation of motion means contain the force, mass into acceleration, or x double dot or y double dot at the equation of motion. So here x double dot y dot. Here similarly here y double dot minus x dot. Set what y dot is given x. Putting that you find the equation of motion in x is this, and y is this. But equation of motion which satisfies this Lagrange equation, or Lagrange t minus b. So del L by del x term here, the del L by del x is x, means L at t minus b, or dv by dx, d minus b by dx is equal to x. So what is b? Integrate 1, then half x square. Similarly, half y square. The total is this. Okay, there is another problem. L is given, you can find the equation of motion. Okay, this is a different problem. A particle is moving under the action of a generalized potential. What is this in the last class? 1 plus q dot by q square. Find the generalized force. We will discuss this type of example. We take velocity dependent potential actually. This one. And okay, we go to the directly velocity dependent potential. Then we will do that problem. Okay. So we already discussed about the conservative forces only, and the Lagrange's equation d by dt del L by del q dot minus del L by del q 0 is only for conservative one. If the force is not conservative, the velocity dependent potential, then we also write similar type of Lagrangian for some problems. Okay. So from general form of Lagrangian equation, we know that d by dt of del t by del qj dot minus del qj is equal to qj. For conservative force, it will be minus del v by del qs, so we become t minus vl. But for okay, del v by del qj, so we get l t minus v. But for a non-conservative system, when sometimes we see this is a velocity dependent potential, we can solve this equation for some particular problems. For those problems for which the generalized force can obtain from a function u qj qj dot. For conservative system, generalized force obtained from u qj. There is no qj dot. But for some systems, if generalized force is derived from u qj qj dot, then we also can follow the Lagrange procedure to solve them and find a or set a Lagrangian. Uh, if u force is derived from qj qj dot, then generalized force can be written like this: qj is equal to d by dt del u by del qj dot minus del u by del qj. So if our potential is given as a function of velocity, then generalized force can be calculated by using this formula: d by dt of del u by del qj dot minus del u by del qj. Okay, uh, where u is BF size potential energy. So Lagrangian or here generalized Lagrangian will be T minus U for velocity dependent potential. For example, the Lagrangian for a charge particle in an electromagnetic field. You know electromagnetic field, Lorentz force F is equal to QE V plus V. Okay. Again, in terms of scalar and vector potential, E is equal to minus del phi by del T, V is equal to del cross A. Substitute these two, we found force. It contains velocity, so it is a velocity dependent force. Here also is a velocity dependent force, conservative one. So by simplifying this term del cross A calculating, okay, we can set this and we find finally an equation. That's what I've done already. This one in form of Lagrangian. This one fx x component of force. So y component similar y z component z. So fx is equal to actually in form of minus del u by del x for dt by del u x dot, where u is equal to this term
Lagrangian.
del of phi v minus a by del v u u phi minus v dot l. So here similar Lagrangian procedure can be followed to get the equation of motion. Mm, mm, Where in place of v you write generalized potential u. Okay. This is the Lagrangian for electromagnetic field. Sometimes it asks in our examination find the Lagrangian for electromagnetic field. Okay, you calculate like this. Okay. Okay. So that problem where a particle is moving under the action of a generalized force, as a generalized potential, then find its generalized force. So how you calculate? You follow that formula: d by dt of del v by del q dot minus del v by del q. This is for velocity dependent potential. For conservative potential, F is equal to only minus del v by del q. But for velocity dependent potential, we have a extra term d by dt del v by del q dot. So using this formula, you can find this. Okay. Okay. Then this is over. Then simple pendulum velocity numerical. Now clear? Hello? This is all about your Lagrangian formulation. Any doubt? No? Okay, we proceed further. Hello?
Yes, sir.
Okay. Next is Hamilton's principle. Okay. Okay. Hamilton principle actually basically what we Lagrangian formulation is on in configuration space. Configuration space normally we know a three-dimensional space has three coordinates. Okay, x, y, z. So 3 degree of freedom. But we already discussed for a particle 3 degree of freedom. That space is known as configuration space. But there are another kind of space which is called phase space. In phase space, we give equal priority to position and momentum. For a particle 3D position coordinate x, y, z, also it has three momentum coordinate px, py, and pz. So phase space for a particle is a 6-dimensional. For a phase space, a particle for n particle system is 6n dimensional. And Hamiltonian formulation is applicable in phase space. Okay. Okay, we discussed that. What is the Hamilton principle? Another system is monogenic system. Hamilton's principle is applicable to all monogenic system, and conservative systems are some limiting case of monogenic system. In monogenic system, all forces except the force of constant are derived from a generalized scalar potential that may be a function of coordinate, velocity, and time. For conservative system, forces are derived from a potential which is a function of position only. But here, for a monogenic system, forces are derived from a scalar function which may be a function of velocity, position, and time. Okay, that is called a monogenic system. Okay, and Hamilton's principle is applicable for all monogenic systems. For simplicity, you can say for a conservative system this is valid, but for it is valid also for a monogenic system. For monogenic systems, Hamilton's principle can be stated as the motion of a system from time t1 to tt is such that the line integration of L dt from t1 to t2, where L is equal to t minus v, the line integral has a stationary value for the actual path of motion. The line integral has a stationary value for the actual path of motion. Okay, this is the Hamilton's principle, where L dt is known as action integral. Okay, since it is stationary, its derivative will be 0. So for actual path, its variation delta I is equal to 0. From this, you can find the equation of motion for every system.
Sir, what exactly mean by stationary here?
Stationary is actually minimum. Most of the case, the minimum. It is your least action principle, what you know in optics or other things. Stationary actually maximum, minimum means constant, but maximum or minimum. Here, general particularly, we consider minimum as the stationary. The integral value should be minimum for actual path of motion. Integral value should be minimum. Okay. There are many paths also, you know, in the actual path. Suppose in distance displacement, you know, displacement is the minimum of the distance. There are many distances you can take, but displacement minimum. Similarly, here integral value is minimum for actual path of motion. There are some techniques of calculus. It is not in your syllabus. We can follow because there are in syllabus written the derivation of Lagrange's equation from Hamilton's principle. Okay, it can be derived. It is given as a quite difficult form. You can also easily derive it. For that, we have to assume a function of yx, f as a function of y1, y2, y dot. Then take its variation. From variation and equating, we get the Lagrange equation. Okay, I will provide its simpler form a note in the next class. It is slightly difficult one for you, I think. Okay. Leave that now. There are two important examples of this principle. Shortest distance in a plane. How you calculate the shortest distance between 2 points. Okay. Suppose the curve joining between 2 points 1 and 2. So what is there may be a number of paths, this one. What is the exact path or actual path? How you calculate this? For that, we use this Hamilton principle. So let us consider a small element of the curve, ds. Okay, but ds, this is a variation x direction, y direction, dy. So obviously ds square will be dx square plus dy square. That is ds is equal to dx square plus dy square root 2 over. If we take dx common, then it will be dx into square root of 1 plus dy by dx square. Take dy by dx y dot. x behaves like t in space because here parameter is t. There our parameter t, here parameter is x. Okay. So dy by dx we take y dot derivative with respect to x. So this is your integral ds. So for actual path of motion, this integral or integration of 1 to 2, this integral should be minimum. Okay. So how you know this minimum? If this will be minimum, we have a condition. What we get from this as analysis, so it is very difficult. Like, from this analysis, we know that uh, for any integral I f y dot x dx is minimum, have a stationary value if d by dx of del f by del y dot minus del f by del y is equal to 0. So here in place of function y dot x is how much? 1 plus y dot. So here f is equal to this one. So there, if d by dx of del f by del y dot minus del f by del y is equal to 0. So we calculate like this. For any integral to be minimum, d by dx del f by del y dot minus del f by del y should be 0. If you want, you can show its derivations here given here. So putting this integration, taking the its derivative del f by del y and del f by y del y dot, f is equal to this one, del f by del y 0, but y dot have a value. Putting we got del f, d by dx of y dot 1 plus y dot square is equal to 0. D by dx of y dot 1 plus y dot square 0. That means this bracketed term is constant. Since the derivative is 0, so this is constant. Again simplifying, y dot is equal to dy by dx. Putting that and equating, we found y dot square is constant is taking c1, like c1 by 1 minus c1 square. That is another constant. Constant 1 minus constant square root over. So a constant. So y is equal to b, dy by dx is equal to a. So y is equal to ax plus b. So actual equation is ax plus b. You know, it is a equation of a straight line. So distance between two, shortest distance between 2 points is a, in a plane is a straight line. Another similar example is minimum surface of revolution. If you revolve a surface around an axis, okay, we found a surface of revolution. For our aim is to find the minimum surface of revolution, or surface, the surface for which the surface area is minimum. It can also calculated by using this Hamilton's principle. Here you consider this is a, let's say this is a strip, small strip of ds rotating around this. Okay, so ds means its value will be like how much? It is at a distance x from the center. So what is its volume? It will be ds this one, and its perimeter will be, if diameter x 2 pi x. Okay, the whole surface will be, if you integrate 2 pi x into ds, so that is to ds is dx square plus d square root over. So you putting this, you found the integral like this, and the minimum surface you found if you use this equation, take its derivative and put, and you find this equation. Take integration simply is the equation of a catenary. Catenary means a flexible chain. This type of thing which you see in front of railway stations. This type of chain. So, these are two important applications of Hamilton's principle. Clear? Now the first part is over. In 1, 2, 3, 4. Then we go for second part.
Sir, please send this handwritten note also. We will-
Okay. But there are so many groups. In which group I will send? You
Sir,
made
IGNO
In the
official.
last group you have sent, sir, in that group.
okay.
Sir, IGNO official group is there. You
Okay.
can get it. And sir, what kind of questions we can expect to have in your exams?
Yeah.
What kind of paper questions we can expect in our exams?
I don't know.
Any-
But generally from this section, actually and derive
Actually,
the
sir, sir, actually,
Lagrange's. Huh?
we are the first batch of MSc PH. Okay, so we do not have any question reference of
Yes, sir.
previous year.
We also don't know the your question pattern. The officials only know. They
Sir,
only
in
know.
general, like derivation of some principle or any example solving.
If long, generally what question asks in our MSc, derive the Lagrange equation from Hamilton principle, derive the Lagrange equation from D'Alembert's principle, or show that the minimum surface of revolution is a catenary, so that certain distance in a plane is a straight line. Okay, or solve the simple pendulum problem using Lagrangian formulation, solve the Arthur's machine problems using Lagrange formulation. And this type of question generally asked in our examinations. Okay.
Okay,
Okay,
so
sir.
by and
Thank
large,
you.
derivatives kind of questions.
Yeah.
Thank you, sir.
And then we go to part 2, which is basically first one is central force. Central force problem. Actually, there are two fundamental things in nature for which actual nature exists. One is the existence of atom. You all know the electrons are revolving around the nucleus inside a atom. Okay, and this was explained by Bohr's theory. And the second one is the revolution of the planet around the sun. Which type of forces are responsible for these two phenomena? Which force is responsible for motion of elec- uh, electron around the nucleus?
Centripetal, centrifugal.
Hello?
Ele-
Centripetal force.
Which one?
Electrostatic force of attraction.
Electrostatic force. Between the two charged particles, you can say electron and positively charged nucleus. Similarly, here gravitational force, not it. But you see, this magnitude of two forces are similar. Here, for electrostatic charge particle force is equal to F is equal to how much? Q1 K Q1 Q2 by R square, is not it?
Yes.
Yes,
Uh,
sir.
but for gravitational, similar F uh, G into M1 M2 by R square.
Ye-
It is
Yes,
Yes,
sir.
sir.
charge into unit mass. Two constant divided by R square. These both type of forces comes under a single force as a central force. Central force means actually it is always directed towards or away from a fixed center and is a magnitude a function of R only. Position of R only. Okay. The force is said to be central force if it is always directed towards or away from a fixed center called the center of force. Okay, this is the center of force here, this is the center of force here. And the magnitude of this force is a function of the distance from that fixed point. That is distance from center of force to the object, maybe electron, maybe planet. If generally we assume that center of force is the origin, then it will be position vector R. Okay. If with the origin center of force, then F is. So since it is always directed towards or away from a fixed center, then what will be the direction? Either in this direction or in this direction. This is the direction of force. What is the position vector direction is this one. So what is R cross F? 0. Hello?
Yes, sir.
Same direction or
Yes, sir. 0, 0.
RF and R cross F is equal to 0. But what is R cross F? Torque. So torque is equal to 0 here. Torque 0 means angular momentum is a constant. Is not it?
Yes, yes, sir.
Yes.
Yes, sir.
So angular momentum for this motion is constant. J is conserved. So angular momentum is a constant. Constant means constant in direction and constant in magnitude. Direction will be constant and magnitude will be constant. See here. But angular momentum on L or J here, R cross P, R is the position vector and P is equal mass into velocity. Velocity in this direction. So across P is always upward. It is a constant here, and according to a thumb rule, across product across P is along this direction, and it is always constant in magnitude and direction is fixed. What it implies? R and V are in the same plane. Okay, so central force motion occurs in a plane only. J is always fixed. So it makes R and V should be occur in a plane. So important point is since J direction is fixed, so central force motion is occurs in a plane. And also conservation of angular movement implies that is a spherical symmetric problem, does not depend on phi. Spherical symmetric problem. For that reason, we use polar coordinate r theta to solve this central force problem. Clear? So central force property is central force problem takes place in a plane. Okay, we go for, but in central force problem generally the center of force of the two objects are needed. So our next our aim is to reduce a two body problem to a one body problem so that we can study easily. Reduction of two body problem to one body problem. So simply think by using the concept of center of mass. Let's see here. There are two bodies, M1 and M2, two particles with position vector on R1 and RT. We can also consider center of mass have a position vector R, capital R. From center of mass system, M1 position coordinate is R1 prime and M2 will be R2 prime. So obviously this distance between M1 and M2 R will be, from this diagram you can say R is equal to R1 minus R2. R1 this direction, R2 and R in this direction, which is obviously R1 prime minus R2 prime. Okay. Now we for a two body, we know it's Lagrangian, right? For this system, what is the Lagrangian? There is a definition: the kinetic energy of a system is equal to kinetic energy of the motion of the center of mass plus kinetic energy of the motion of system about center of mass. You can also prove in M1. So kinetic energy of a system is equal to kinetic energy of center of mass plus kinetic energy about center of mass. So about center of mass coordinates are prime coordinates. So center of mass kinetic energy means its whole mass m1 plus m2. Center of mass is the point where we assume that whole mass is concentrated. So m1 plus m2. What is it? And its position vector r. So its kinetic energy will be half m1 plus m2 plus capital R dot square. So half m1 r1 prime square and half m2 r2 prime dot square. This is the about center of mass. Let's say potential energy V. So this is Lagrangian is equal to T minus V. Again we know that a body is balanced about its center of mass. Body is always balanced, that is product of mass and position vector of individual particle. If you take its sum, it will be 0 at center of mass point. Now take this sum. There are two particles. So m1 r1 prime plus m2 r2 prime is 0. From this you found r1 prime is equal to minus m2 by m1 r2 prime. Now put in place of r1 prime this value. We get r2 prime is equal to minus m1 by m2 plus r. Okay, slightly simply manipulation. You can do this. Now we get the kinetic energy in this form. By substituting all this, we get this form. Half m1 m2 r dot square is center of mass kinetic energy plus half, that is m1 m2 by m1 of m2, which is known as reduced mass. Why it called reduced mass? Because it is less than both m1 and m2. And general formula I know 1 by mu is equal to 1 by m1 plus m2 for reduced mass. Using this we found this is the equation of unit r dot square. For a Lagrangian will be this. But if you take the Lagrange equation of motion, we found in capital R, we found r dot is a constant. But in small r, you have an equation like mu r dot is equal to fr. Since r dot is a constant, we can remove this from the equation of motion and we can only say this our equation approaches to this kinetic energy of mu r dot square minus Vr. Okay. In this way, a two body problem reduced to a one body problem. Okay. Then we go for classification of orbit under central force motion.
Excuse me, sir. Sir, it's a given R is a cyclic. What is the meaning of that cyclic?
Okay. So I'm discussing fast cycling. Then we go for this. There are so many things in your course, but it is not possible to discuss everything in 2 hours. Cyclic one. If a coordinate does not appear in the Lagrangian, we call it a cyclic coordinate. Okay. Lagrangian contains many coordinates. If a coordinate does not appear in the Lagrangian, we call it a cyclic coordinate. We know that from a conservative system, Lagrangian is equal to T minus V. Okay. And del L by del Qj dot is equal to del by del Q dot T minus V. Since V does not contain velocity, so it will be Pj. Del
Yes,
T
sir.
by del Qj dot is equal to Pj. Okay.
Yes, sir.
So if you put in the Lagrange's equation, del L by del Qj dot is equal to Pj. This is the generalized momentum. If a coordinate is Qj, then Pj you can calculate del L by del Qj dot. It is general formula. Pj is equal to del L by del Qj dot. Pj is called canonical momentum or conjugate momentum, and it related with small qj as cap. Pj is equal to del L by del Qj dot. Okay. If the Lagrangian of a system does not contain a particular coordinate Qk or Qj, then for that system del L by del Qj dot or del L by Qj dot will be 0.
Sir, anything dependent on velocity, that will be generalized in conjugate momentum?
No. Conjugate momentum is associated with coordinate according to this formula. If Pj is equal to del L by del Qj dot, if Qj is a generalized coordinate, then its corresponding momenta, which is calculated by this formula, Pj is equal to del L by del Qj dot, is known as conjugate momenta. Okay. If a Lagrangian does not contain a coordinate, then its del L by del Qk 0. If Qk not contained in the Lagrangian, then del L by del Q is 0. And we call that coordinate Qk is a cyclic or ignorable coordinate. Suppose in your simple pendulum case, simple pendulum Lagrangian is equal to how much? T minus P, T will be half m theta dot square. We see half m theta dot square minus L minus L cos theta, something like this. So here R is absent. Isn't it? There is no R coordinate. Hello? So for a simple pendulum, R is a cyclic coordinate. There are two coordinate coordinate system, R theta, but for a pendulum only equation Lagrangian contains theta and theta coordinate. So it does not contain R coordinate. So R is a cyclic coordinate for simple pendulum. Clear? Hello?
Yes, sir. Yes, sir.
It does not appear in the Lagrangian. So if it does not in the Lagrangian del L by del Qj 0, you put in this Lagrange equation. If Qj does not appear, this term becomes 0. So this term is equal to 0. That means for del L by del Qj is how much? Pj. So del Pj by del T is equal to 0. That means Pj is a what? If derivative of Pj is 0, Pj is constant. So for a cyclic coordinate, corresponding momentum or conjugate momentum is a constant of motion. So why it is important? For a cyclic coordinate, its conjugate momentum is a constant. Okay. So actually we see if time is cyclic, if time does not appear in the equation Lagrangian, total energy is a conserved quantity or corresponding momentum is energy which is a constant. If some translational coordinate is cyclic, corresponding linear momentum is conserved. If some rotational coordinate is cyclic, corresponding angular momentum is conserved. Okay. So generally rotation cycle means spherical symmetric or spherical symmetric body, all components of angular momentum are conserved. But if the system is symmetric on z axis, only Lz is conserved. Then thing is conservation of energy.
Sir, if vice versa is also true. If it is conserved, then it is cyclic.
Yes,
Can
yes.
we say that?
That is
Okay.
the Noether's theorem we discuss in the next class. In our paper 2, we have class in Noether's theorem.
Okay.
Every that is associated with symmetry. Every symmetry is associated with conservation. What you can say. But here, in terms of mathematics, if Qj is cyclic, Pj is conserved. If Pj is conserved, Qj is cyclic. So one important point is conservation of energy. Actually, where actually that uh, where from the general from Lagrangian is a function of Qj dot t. Okay, it is important thing. Lagrangian is it is defined in configuration sense, and it is Qj dot t. But Hamiltonian is derived in phase space, and phase space means their coordinates are Qj, Pj, t. No Q dot or Qj dot. Uh, So it is phase space Qj Pj function of Qj Pj t. If asked to write Hamiltonian, you have to convert all Qj dot to Pj. There is a formula. This formula we derive. But second thing is we have write Hamiltonian in terms of Qj and Pj, and Lagrangian in Qj and Qj dot. Okay. So L is a function of this general Qj velocity t. So dl by dt is how much? Like your formula, f is a function of x, y, z, and df by dt is equal to del f by del x, dx del f by del y, dy del f by del d dt. Similarly here, but there are many coordinates. Qj means here q1, q2, q3, and qj dot means q1, q2 to q3, and okay. So I write like this. Sum means 3 and 1 to 3 and this. But from Lagrange's equation we have d by dt of del L by del Qj dot is equal to del L by del Qj. D by dt of, okay, so put that. So del L by del T is equal to d by dt of del L by del Qj dot. Here del L by del Qj in place of del L by del Qj, put that. In terms of you want d by dt of del L by del Qj dot, and dQj by dt is Qj dot. Del L by del Qj dot, del Qj by del T plus del L by del T. This equal to d by dt of, here you see the d by dt of this into Qj dot plus del L by del Qj dot into d by dt of Qj dot, and derivative of u into v plus u into derivative of v. That means derivative of u v, derivative of u del L by del Qj into Qj dot plus del L by del T. But del L by del Qj dot is Pj, you know that. So this formula becomes Pj Qj dot plus del L by del T. Or you can write this summed over Pj Qj dot minus L is equal to del L by del T. If you take this to this side, or okay, and equator, you take this one to this side, and it is to left side. We found that's the same. Okay, we take only this left side to the right, and so it will become 0. Here Pj Qj dot minus L. Okay, that quantity is known as Hamiltonian H, which is your total energy for a conservative system. Hamiltonian is equal to total energy H. H is equal to Pj Qj dot minus L, is known as Hamiltonian. So sometimes Lagrangian is given and asked calculate Hamiltonian. You can calculate using this formula. Here J refers to number of independent coordinate or generalized coordinate. Okay. But another thing is L is a function of Q dot T, but H is always a function of Q P T. So first you write according to this formula, then convert all Q dot to P. Okay. So Pj is equal to del L by del Qj dot in formula. If you calculate this quantity summed over Pj Qj dot, you see using your Euler's theorem, you found what you know in your Class-2, you found this will be 2t. So H is equal to 2t minus L. But L is equal to t minus v. If you substitute all, you found H is equal to total energy E. So for a conservative system, Hamiltonian is represent the total energy. H is equal to T plus V. And it is also, you know, in your quantum mechanics, which is a Schrodinger equation, comes from H psi is equal to T plus V psi. It is applicable for conservative system there. Okay. Here, so this is a Hamiltonian, and it is okay. Next, we go for classification of orbit. For central force, you know, it is a function of r only, and its direction is along r cap. So you can write that force is equal to function of r into r cap, or since the function is equal to minus del v by del r, conservative field, so without r cap del v by del r. But Lagrangian of a system in terms of plane polar coordinate is equal to half m r dot square r square theta dot minus v r. For central force problem, we use plane polar coordinate. This is the Lagrangian one. Okay. So from this Lagrangian, you can get the Lagrange's equation of motion, which tells you del L by del R, you calculate this, del L by del R dot, calculate this, and finally we got this m r double dot minus j square by m r q is equal to f r. Okay. But in Newtonian mechanics, we know that force is equal to mass into acceleration is the equation of motion. But here there is an extra term. So if you take to the right hand side, it will be added with this. So we can say m r double dot with this, which you take a general force known as a effective force, no? Or fictitious force. Okay. We take matching with the, Newton's mechanics. F is equal to ma. We take is this plus this force is known as a fictitious or effective force. Fr plus j square by mr cube. J is your angular momentum. J value, if you calculate, it will be m r square theta dot. And we use here J is equal to m r square theta dot. So putting this m r square theta dot, we found FR will effective force will be m r theta dot square by r. And we assume that this effective force is comes from the effective potential by obeying the formula F prime r minus del V r prime r by del r. Taking this integration, you can find that quantity. So VR will be effective potential will be GR plus J square by 2m r square. The total energy E plus V becomes half m VR plus this or half m r dot square V prime r. It is just like a single particle system. Kinetic of the particle and potential of the particle. So in this way, we can find the effective potential as an orbit. One thing, tell me, when you throw a stone to off, you see it after moving some distance, it will fall down. What happens here? Why it fall down from this distance? Hello? When you throw a stone, it will go off over some distance. After it fall down. What happens
Due
here?
to
Hello?
uh,
What happens?
due to the action of gravity, sir, it will fall down.
So why not
because,
from here? Gravity is always present. Why not from this point? Why not from this point?
At that point, the initial velocity will keep on decreasing due to the gravitation force.
Yeah.
And
Then
at
so
that point,
this
it will
point
become
velocity is
zero.
equal to zero.
Yes, sir.
This point velocity is equal to zero. That means kinetic
Yes,
energy,
potential energy.
total energy becomes potential energy. Okay.
Yes, sir. Potential
Total
energy.
energy becomes potential energy. Another
Energy
situation.
extraction.
Okay. Suppose I am rolling a ball on the floor. After it covering some distance, it will stop here. Isn't it? After moving some distance, it will stop here. So what happens here?
Frictional force.
Due to
Why?
friction.
Friction is okay. Opposing this
Oh.
like gravitation here. But what happens this point? Total energy becomes kinetic will how much here? If it becomes total energy equal to potential. Isn't it? Both the
Yes,
two
sir.
cases
Yes.
have a total energy becomes potential. But in one case, motion stops, otherwise here motion changes its direction of motion. So when total energy approaches potential, a body should change its direction of motion, otherwise its motion stops. Okay. Uh, so when the body is moving,
Yes.
to keep it is a dynamic body, it should change the direction of motion. So at a point where body changes its direction of motion, only characteristic is at that point total energy is potential energy. Totally, yeah. And that point is known as, where direction changes, that point is called, where the direction of game is changed, that point is called, what point? We call the dash point of the match. What point? Where direction?
Turning
Turning
point.
point, yes. So the characteristics of turning point is total energy is equal to potential energy, and that
Potential.
body changes its direction of motion. Okay. So whenever you see body changes its direction of motion, then its total energy is potential. And this is the actually main thing for the orbit under inverse square law of force. You see this type of figure in the front page of some books. Is important one, and the important thing is that inverse square law of force. Inverse square means 1 by r square. Inverse square, we take attractive, negative sign is for attractive. Attractive inverse square law, because this law is your gravitational force, planets are revolving around the sun, obeying this kind of law. Attractive inverse square law. So we have to check what happens to the orbit under inverse square law of force. Inverse square law, like minus k by r square. From this, if you calculate the potential taking its integration, it will be minus k by r. So for inverse square law of force, force is equal to minus k by r square, potential minus k by r. So effective potential will be what we written, Vr plus j square by 2mr square. It becomes minus k by r plus j square by 2mr square. Okay. Now plot v prime r and r. This is the plot. This one, v prime r and r. So now separately we can plot the separate plot of minus k by r, plotting like this, and this is j square by 2mr square. Two terms separately you can also plot. Okay. We have to now check the orbit, or we can say under this force. For that, we take some lines of definite energy. Here line E1 having a positive energy, E2 0, E3 some negative energy, E4 minimum negative energy. You cannot go further where the curve touches lastly here. And we use that principle when total energy becomes potential. In the total energy line, it is potential curve. Each intersection point represents total energy is equal to potential energy V prime. And so these points are the turning points of the motion. Okay, is it clear?
Yes, sir.
So we can plot easily this. So let us consider the case 1. We take the E1 case. Case 1, total energy E1 is greater than 0, means positive energy. Since positive energy, we see it has only one turning point. Not it. So clearly the particle can never come closer than R1, because here it turns its motion, cannot go further. Total energy potential means it's, if it is coming from this side, it will move like this. It does not go further. Okay. So this distance R1 is below R1. If R less than R1, then particle cannot go through that region. Because R less than or V prime exceeds C1 is another condition. So it might become imaginary velocity. On the other hand, there is no upper limit. But there is no upper limit where it can go further anywhere. So your motion is not bounded for this type of motion, and you know this type of motion is the
Hyperbola.
hyperbolic motion.
Yes.
Uh, A particle will come from infinite strike repulsive barrier and again back to this and turning. And this is the distance measurement occur. So this distance will be how much? Half m r dot square over distance, because this was kr, this is v prime r. The difference it is not required. Okay. And the second thing, when E2 is equal to 0, in second case, E2 is positive with the C. So it touches at one point or also one turning point, not it. So this case is similar to the E1 case. Isn't it? Hello?
Yes, sir.
It's a similar case. So then we go for third one. Okay. Where is third one? Okay, wait. I am third one. Third one. Third one. This is classification of orbit.
শুভ নাই
Okay. I'm thinking that no, that one. Ventral force motion. Where is third one? I have written somewhere. For square law orbit. Sorry. Okay. Like classification of orbit. Second slide is visible. Hello?
Yes, sir.
Then we consider case 3 and case 4. This is the case 3. In case 3, energy is less than 0. Okay, third one, this case. And here, how many points it touches? The potential energy curve?
2 points.
2 points. So there are 2 turning points. Okay, if you say this is R1, this is R2.
Okay.
2 turning point means motion is bounded. If you call a particular case, but we can say motion is bounded between 2 distances, one R1 and R2. Okay, or if you particularly plot this is that figure. So motion is bounded between these 2 circles. Motion comes like this, comes like this. Ellipse is a special case of this. Okay, the 2 bounding point. Then we go for case 4. Case 4 here, see, only one turning point and at the minimum. Isn't it? Or if you will see, if I take this line, if I take R1, this one, R2, this one, R1 increases, R2 decreases. Isn't it? Here R1 increases, R2 decreases. And here actually R1 is equal to R2. So if 2 radius become same, then it is a
Circle.
Circle. So case 4, there is minimum energy, it will be a circle. Motion is a circle. We can also calculate from mathematical form that at that point f prime r is equal to 0, but L is 0, f prime r is fr plus mr theta dot square. If you calculate, you found fr is equal to minus mr theta dot whole square by r. Okay. So this is elementary condition for circular orbit. So these are the 4 cases of orbits. Okay. We exactly next go to for Kepler's problem. Okay. Actually, in what's called law of force, Kepler studies the motion of the planets around the sun and give 3 laws, which is known as famous Kepler's laws. And the first law is Kepler's law of planetary motion is motion of the planets around the sun is governed by three laws known as laws of planetary motion, and first law is also known as law of elliptical orbit. Every planet move around the sun in an elliptic orbit with sun at the one of its foci. Plural of focus. Ellipse, there are 2 points or 2 focuses are called foci. So planets are revolving around in such a way that sun is at one of its foci. Law of second, which is known as law of area. The radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. That is, aerial velocity of a planet is a constant. Okay, so the radius vector drawn from sun to planet cover equal area in equal time, which is actually conservation of aerial velocity, general property. And third one is the square of the time period of revolution is directly proportional to cube of the semi-major axis of the elliptical orbit. The square of the time period of revolution is directly proportional to cube of the semi-major axis of the elliptical orbit. T square proportional to a cube. Okay. We go for derivation of it, deduction of first law. For first law derivation, we use the first integral we know as energy, a kinetic energy plus potential energy. We got this one, half m r dot square, and from r square theta dot, so you can found this term. We already found this energy is equal to this one. So from this you can calculate r dot is equal to root over of this. Only simplification. Then from r dot is dr by dt, or you can write dt is equal to dr by this. But again, j angular momentum is m r square theta dot. So theta dot is equal to j by m r square. Theta dot means d theta by dt. Okay, j by m r square, so dt is equal to m r square by j d theta. Comparing two dt's, equation 1 and 2, you can write m r square by j d theta is equal to dr by root over of this. So d theta is equal to j by m r square into dr by this. And simply rearranging, you can write d theta is a rearrangement r square. We got a form. But for inverse square law of force, F is equal to minus k by r square, so V is equal to minus k by r. Putting minus k by r here in place of V, we got d theta is equal to this. This is the general equation. Now we want to solve this. For this, we use one substitution. U is equal to 1 by r. So that obviously du is equal to minus 1 by r square dr. Now putting this u in place of 1 by r and du in place of minus 1 by r square dr, we got this equation. Du by this. Or integrating this, we got the theta is equal to minus this. Theta prime is a constant of integration. So theta becomes theta prime minus this. But what is this equation? If you take, you see 2me by j square, 2m j square u minus u square, it's quadratic in u. This equation just like alpha plus beta x gamma x square. X is u. So alpha beta x gamma x square is this. So alpha plus beta x plus gamma x square. If you slightly rearrange, we can find the integration alpha beta gamma will be this. Minus cos inverse y by c. Or y by c means this one. So comparing our case, what is the value of alpha, beta and gamma, and putting this, you found this is your value. Integration will be this much, cos inverse this one. So we got theta minus theta prime this, or this is equal to cos theta minus theta prime. And cos using cos minus x is equal to cos x. From this you find u is equal to mk by j square, or u is equal to 1 by r. So 1 by r is equal to mk by j square, 1 plus 1 by 2 j square mk root over cos theta minus theta prime. Comparing with your general expression, 1 by r is equal to c constant into 1 plus c cos theta is the equation of a conic section where E is known as eccentricity. So comparing this, we can say eccentricity is 1 plus 2 j square E by mk square. So if E is equal to greater than 0, then small e will be greater than 1, and it is a hyperbola. For For the case 1, energy, positive energy, when E is equal to 0, E is equal to 1 and is a parabola. Okay. When E is negative, small is less than 1 and is a ellipse. When E is equal to 0, capital E is minus mk square by 2j square and it is a circle. This is the classification of orbit. What we already get from the classification of orbits, this pictorial notation. Okay, it exactly matches with Kepler's law derivation. So our case for motion of planets around the sun, it is a elliptical orbit and the energy is negative, eccentricity -1. Okay, and derivative of second law. For central force motion, angular momentum J is a conserved quantity, but angular momentum J is equal to m r square theta dot. If m is mass, it can value some kg, you can take half kg, 1 kg, 5. If you put m is equal to half, then this equation becomes J is equal to half r square theta dot. Okay, but angular momentum is a conserved quantity in central force motion, so half r square theta dot is a constant. But what is half r square theta dot? If you take its radial velocity, if the radius vector r rotates through an angle d theta in time dt, then the area swept out in dt is given by half r into r d theta. This area of this region, which is half r square d theta. If you take derivative with respect to time, dA by dt is equal to half r square d theta dot. But half r square theta dot is constant, so dA by dt is constant. Aerial velocity is constant. The second law. Then deduction of Kepler's third law. So Kepler's second law is the nothing but conservation of angular momentum. Okay. Conservation of angular momentum. Third law. From an elliptic orbit, the semi-major axis is one of sum of two apsidal distances r1 and r2. Okay. For ellipse case, actually, this is r1, this is r2. So if you add this r1 plus r2, it will be this, and it half will be semi-major axis. By definition, the radial velocity is 0 at these points. And at R1 and R2, you know, it touches the total energy becomes potential. Total energy becomes potential and kinetic energy term 0. R dot 0. So at turning point, R dot 0, obviously. So in expression, total energy, if I may discuss this, so at turning point, this term 0, so only j square by 2m square plus br. So at R1 and R2, energy will be j square by 2m R1 square plus br and j square by 2m R2 square plus br. Okay. But for central force motion, Vr is equal to minus k by r. So if you put here, total energy becomes j square by 2m square minus kr. E minus this is equal to 0. Or we can write it as a quadratic equation in terms of r. This equation. And the two roots of this equation actually two abscindant distance r1 and r2. But again, semi-major axis what we told r1 plus r2 by 2. But here in a quadratic equation there are some rules of the root. You know, for a quadratic equation, roots are minus b
Plus minus root over of b square minus 4ac
by 2a. So if you add two roots, what will the value? If add two roots, there are two roots, one plus root, one minus root. If you add these two,
minus b by 2a.
2a.
two add this, two cancel, minus b by a only. Isn't it? Add
Minus
this,
b by a.
plus minus cancel. So minus
Yes,
b
sir.
by 2a plus minus
Minus
b by
b by 2a, that is b by a.
2a.
Minus b by a.
Minus b by a. So what is b here? Ax
This is the coefficient of
K by ER.
k
by
by
e.
a
K
is
by
b.
E.
A
by
is
a by
one.
e.
So minus b by a is equal to minus k by 2e. Isn't it?
Yes, sir.
Okay. Because the R1 plus R2 by 2. The half is come from that. So, okay. So now from the equation, from this you can say E is equal to how much? Minus K by 2A. But the eccentricity we got 1 plus 2 is A square by MK square root over. But E is equal to minus K by 2A, put here E is equal to minus K by 2A is equal to minus J square by MK. Again we know that dA by dt is equal to half r square theta dot. Half r square theta dot is equal to J by m r square. If r square cancel, J by 2m. It dA by dt. So what is A? So the area of the orbit is founded by integrating over total time period tau. So A will be calculated in integral 0 to tau, which will be J by 2m tau. But since it is a ellipse, its area will be pi AB. Isn't it? Area of ellipse pi AB. So we are writing area pi AB. So J tau by 2m is equal to pi AB. So tau is equal to 2m by J pi AB. But for ellipse, its B and A are related through eccentricity. B is equal to A into 1 minus E square root over. Where E is equal to 1 minus J square by M square root over. We calculated already. Using this, we found B is equal to A to the power half into square root of J square by MK. And putting this in here, we found tau is equal to proportional to A to the power 3 by 2, tau square proportional to A cube. This is your Kepler's third law. About motion of a planet around sun in a two-body problem. Okay. For exact motion, you can replace m by reduced mass, mm by m plus m, and for the attractive gravitational force, force is equal to minus g mm by r square. Actually, you know the magnitude g mm by r square, but it is actually attracting force, and total force is equal to minus g m capital M by r square. So from this you can calculate k. We take minus k by r square. So your k will be capital G, small m, capital M. Okay. Put this. We have found tau, exact form of tau. Tau is proportional to A to the power 2 by 3. And Kepler's third law. Clear?
Yes, sir.
Yes, sir.
Next one
Yes,
is
sir.
Bertrand's theorem. No, here. Theorem for closed orbit. Okay. For central force motion, we know that one kind of closed orbit, circular orbit, is obtained only when the effective or pictorial potential is minimum. We already see that one type of closed orbit when minimum potential or circular orbit. So if potential is minimum, how you calculate? Then its derivative will be 0. Okay, that of del alpha and del r 0. So taking its derivative 0 and putting del v by del r minus fr, we found f at that point fr 0 is equal to minus j square by m r 0 cube. Okay. Equation tells that must be attractive for circular orbit. Minus sign represent attractive. We know that total energy is equal to kinetic energy plus potential energy half m r square vr plus j square 2m square at r is equal to r0. Okay, that point on circular orbit is a turning point. So here r dot is equal to 0. So only E is equal to vr plus j square by vr0 j square by 2mr square. For v prime minimum, a double derivative will be greater than 0 with the case of stable circular orbit, and a v prime is maximum in case of unstable circular orbit. As for a stable circular orbit, if this 0, we have the v prime, we can double taking derivative, double derivative, we found this condition. Okay, but from equation 1 we have j square equal this. Putting in place of j square and cancelling, we found for stable orbit r by fr del f by del r r0 is less than minus 3. But putting fr minus k r to the power n power law form, if inverse per power law, r is n equal minus 2. We found 3k r n minus 1, or n, k is a positive constant, n minus n or n greater than minus 3. A power law attractive potential varying more slowly than 1 by RQ, thus capable of forming circular orbit. It a condition this one n greater than -3. If circular orbit is stable, then a small increase in the particle energy above value results only a slight variation. For a stable orbit, slight change gives slight variation. If we exactly we see, taking some conditions, we found that two kinds of orbits are actually circular. If one is the only central forces that result in the closed orbits for all bound particles are the inverse square law of force, 1 by r square, Kepler's law, and Hooke's law. Hooke's law means harmonic oscillator, force proportional to x or minus x. So these two laws gives you a closed orbit. One is your inverse square law, motion of the planet and sun, and another is your Hooke's law. Okay, this is about thing. Next we have scattering. Okay, I'm seeing anything left. Plus problem 2. The next we go for scattering. Scattering in a central force field. You already know about Rutherford alphabet in scattering, which actually gives the confirmation of nucleus. Existence of nucleus is confirmed by the Rutherford scattering. Okay. We can calculate or do its mathematical part. Scattering in a central force field. So the procedure for describing scattering phenomenon same whether the mechanics is classical or quantum. Procedure is same. Okay. If one body formulation, the scattering problem is concerned with the scattering of particles by a center of force. Okay. Consider a uniform beam of particles incident on a center of force. All the particles of the beam have same mass and same energy. But force between the incident particle and the center of force falls up to 0 for very large distances. Proportional to 1 by r square. When a particle approaches center of force, it will be either attracted or repelled. So its path will deviate from the incident straight line trajectory. Okay, what other force is? If it is a positive charge particle, it will be repelled by the positively charged nucleus. If it is negative charge particle, it will attract. After passing the center of force, as the particle goes away, the force acting on the particle will eventually diminish. In general, the final direction of motion is not same as the incident direction. So why call it scattering? Suppose there is a center of force, no particles are coming, approaching toward motion, then after this they will repel attract like this. So there is a deviation, the scattering process. Scattering. Terms related to scattering very important. There is the intensity or clock density. Intensity of the beam defines the number of particles crossing per unit area normal to the direction of the beam in unit time. Okay. It's the number of particles crossing per unit area. Scattering angle, the angle between the incident and the scattered direction of the particle. Another is the impact parameter. Okay. We have a term impact parameter. Impact, if we draw a perpendicular on the direction of the incident beam from the scattering center, the length of the line is called impact parameter. In other words, impact parameter is defined as the perpendicular distance between center of force and the incident velocity. Perpendicular distance between center of force, suppose moving like this, the center of force, it comes and moves like this. Okay, this distance, if you draw a perpendicular, and this distance is your impact parameter. Scattering cross section. Consider a uniform beam of particle moving with flux density I0 toward the scattering center presents an area d sigma perpendicular to path of the beam. So that whatever particle hit d sigma are scattered in the solid angle d omega. Okay. Suppose there is a region d sigma, particles are area scattered, how much fall through the d sigma, they are absorbed through d omega solid angle. All are, because this side all are scattered, they are all absorbed by this region. Okay. Number of particles scattered from d sigma per unit time will be incident intensity I0 into d sigma, and number of particles scattered into omega per solid angle or per unit time, it will be I omega d omega. So both should be same, since there is no creation and absorption of this particular beam. So both the incident beam must be equal to the scattering beam. I0 d sigma will be I omega d omega. So d sigma by d omega is will be I omega by I0. This quantity d sigma by d omega, or we commonly known as sigma omega, is called the differential scattering cross section. Differential scattering cross section, or simply scattering cross section for scattering in omega direction. We have to calculate this I omega by I0. So the differential scattering cross section is the ratio of the number of scattered particles per unit solid angle per unit time to the flux density of the incident particle. The cross section for scattering in a given direction is given by sigma omega d omega is equal to number of particles scattered in solid angle per incident intensity. You can also calculate total scattering cross section by integrating this. But in particular, we use scattering cross section, this from d sigma by d omega expression. The name cross section is deserved in sigma. It has the dimension of an area. Cross section has the dimension of area, so why it is called scattering cross section. For any given particle, the constants of the orbit and hence the amount of scattering are determined by its energy and angular momentum. Here we can express angular momentum in terms of energy and so-called impact parameter. So we also express angular momentum in terms of energy and impact parameter. If V is the incident speed of the particle, then kinetic energy will have mv square. Okay, and angular momentum mvr. So but we have mv0 is equal to 2mv root over. So now you see equation B, we get J is equal to S into 2mv root over. From this equation, here you get mv0 2mv root over. But here we get J is equal to ms into v0, but mv0 this one, so S into 2mv root over. Once E and S are fixed, the angle of scattering is then determined uniquely. We have to find first E and S, then angle of scattering. But in quantum mechanical case, one cannot unequivocally predict the trajectory of any particular particle, since it is probabilistic in nature, so we cannot exactly determine the orbit. Rather we call probabilistic, probabilities of scattering in various directions. With the figure, okay, with the S is the impact parameter distance, it is ds, distance from this to d sigma, through which particles on both they are scattered and they all absorb through d omega, region solid angle. Okay, with the scattering angle, this capital theta. This is the figure to calculate different quantity. As the force is central, there must be completely symmetry about the x-axis of the incident beam. Spherical symmetry problem, central force. So it is symmetry, incident beam. And a solid angle, you know by definition, it will be dA by r square. Area you can calculate 2 pi r sin theta or d theta. This area will be r sin theta, this is radius. This is r, so r sin theta. 2 pi r sin theta into dA. What is this? 2 pi. So dA by r square. There are 2 pi r sin theta r, and r d theta by r square plus 2 pi sin theta d theta. So number of incident particle will be I0 2 pi ds. Number of scattering will be 2 pi sin theta d theta. We have to find its ratio I sigma by I0, which is scattering cross section. Well, this is your equation. I omega d omega is this, but I0 this sigma. So from this you can calculate sigma scattering cross sigma theta is equal to minus s by sin theta ds by t theta. It will give the differential cross section on the scattering angle theta. The expression, normal expression for scattering angle minus s by sigma theta means d sigma by d theta is equal to minus s by sin theta. S is impact parameter into ds by d theta. Okay. Then we go for exact scattering, which is Rutherford scattering. এটা জানি হচ্ছে না নাই স্ক্যাটারিং তো হ্যালো
Yes, sir.
Yes, sir.
Devlina, any question? Oh, okay. So these are the terms. Now we go to exact the problem. Rutherford scattering cross section. Okay. It is slightly difficult to calculate. But now come to this. It will be easier for you. Rutherford scattering cross section. Here actually Coulomb field scatter is centrally nucleus. The Rutherford scattering positive charge particle of charge Zd and mass m is scattered by a heavy nucleus of charge Z prime e. We have a nucleus and we strike another nucleus with it. If the existing nucleus which is the center with Z prime e, then we bombard it with another having charge Zd and mass m. The nucleus is raised during the collision. We assume that nucleus is this nucleus Z prime is rest, and this is your called charge particle. Z is a charge particle. Okay. Suppose the positive charge particle moving toward the heavy nucleus with initial velocity v0. As the particle approach the nucleus, there is a repulsive force increases, and the motion of particle change from a straight line path since the positive repel, and force is Coulombic force, you know, and the magnitude will be 1 by 4 pi Zd into Z prime e by r square. These are Coulombic force. So equation represents charge particle moving under this repulsive force. For general expression of force, we know that minus k by r square. So comparing this, we can say k is equal to how much? 1 by 4 pi Z by e square. This is our k. Then go to the formula. We know that for charge particle moving under inverse square law of force, the equation of orbit is motion under inverse square law of force. Motion orbit 1 by r c into 1 plus epsilon cos theta minus theta prime, where c is mk by j square and epsilon, which is actually eccentricity, yeah? 1 plus 2 is j square by mk square. Taking constant of mitigation theta prime is 0, we can take it 0, so it will be c into 1 plus epsilon cos theta. What is the value of c? If you compare, c is equal to m k by j square. K is already found here, so it will be m by j square into this quantity. Okay, we found the value of c. Again, eccentricity 2 is j square by mk square. Okay, 2 is j square by m, 1 by k square value we found from this. But angular momentum is related to an impact parameter, but we see j is equal to s into 2me root over. So E is equal to 1 plus, in place of j you put 2 s into me root over. So finally we got an expression E or eccentricity in terms of Es. Since 1 plus some square, so it is always positive. If x is negative, x square is always positive. X is positive, x square is always positive. So it is always positive term. So 1 plus something, we know root over 1 is 1. So 1 plus something root over is greater than 1. So here we found eccentricity is greater than 1. So the path is a hyperbola. Okay. Now orbit equation 1 plus epsilon theta, we'll put the value of c epsilon and we got the equation. Then we calculate the exact scattering angle. Since the hyperbolic path is symmetric about the direction, path is hyperbola, so we know the hyperbola is symmetric about the direction. So here angle theta, scattering angle is equal to pi minus 2 alpha. We have to measure this scattering because incident comes like this and go like this. So this is scattering angle or this is the scattering angle. If you from this side or it comes like this, so scattering angle this and its value will be how much? This plus this plus this is equal to how much? 2 alpha plus theta is equal to pi, is not it? This angle is your pi. So this theta is equal to pi minus 2 alpha. I have written there. So here alpha is the angle between direction of incoming asymptote and the periapsis. So from this you can find alpha is equal to pi by 2 minus theta by 2. Further, for symmetric direction, r tends to infinity, theta tends to alpha. If this r is infinity, with r small theta larger, r large theta decreases. Okay, or this point is moves closer. So at r tends to infinity, theta alpha. That's it. Theta becomes alpha. So at that condition, we can say 1 plus epsilon cos alpha is equal to 0. Because equation 8 you see 1 by r infinity means 0 is equal to c into 1 plus epsilon cos theta. 1 plus epsilon cos theta is equal to alpha, so it's 0. So cos alpha is equal to minus 1 by e, and the alpha is equal to pi by 2 minus theta by 2. So cos pi by 2 minus theta by 2 sin theta by 2 is equal to minus 1 by e, or cosec theta by 2 1 by this is equal to minus e. So cosec theta and 1 plus cot square theta by 2 is equal to minus e. Squaring both sides and simplifying, we got cot theta by 2 this, or s impact parameter is equal to into cot theta by 2. So scattering cross section, which from formula minus s by sin theta and ds by d theta, from this expression ds by d theta you can calculate and found the sigma theta of scattering cross section is equal to this, inversely proportional to sin 4 theta by 2. This is known as Rutherford scattering formula. Very important question, and derive the Rutherford scattering formula, and you write starting from this equation, write this. Okay, but you have to remember a few things. Okay, is it clear? Very important question. Scattering cross.
Sir, this question might come to the exam.
Yes.
Yeah. Okay. Okay. Any doubt? Tell me. I think this is sufficient for today's class. We have only one thing left, small oscillation. We discuss in the tomorrow.
Okay, sir.
Any doubt?
No, sir.
No, sir, it's clear. Can you please share the notes through WhatsApp?
Okay. I will share.
Sir, after the all classes are over, can we have one doubt clearing classes near the exams? No.
Yes.
Means apart from IGNO planned classes.
Okay. You read this, and if you have any doubt, you can ask me, or you can ask me in the next class, or okay, we will take a class. No problem.
Thank you, sir.
Okay.
Sir, thank you. Derivatives are very well established and extensive.
Excuse me, sir. Sir, can you suggest a book having little bit of detail, because the IGNO study material is very very compact. It's not having.
Actually, Gupta Kumar Sharma book, which is written is very easily you can understand from
Which book? Which book?
Classical Mechanics by Gupta Kumar Sharma. Three people, Gupta, Kumar, and Sharma.
Gupta, Kumar, and Sharma. Okay.
Goldstein is the reference book. It is all are following Goldstein.
Okay.
It is little difficult to understand. Reading.
Gupta, Kumar, Sharma will follow, sir.
Yeah.
Okay. Thank you, sir.
Classical mechanics, right, sir?
Yeah, yeah.
Uh,
Any, anything else?
so one thing, sir.
Yeah.
Many of us are veteran member in the forum. Um, we had our graduations long back.
Yeah.
How should we approach the courseware? What are the prerequisites to understand with ease, and there are limitations in digital learning, so we have to overcome those issues also. And it is not always possible to connect you or any other professors. So
Yeah.
what are the pre-readings that, because your I mean session was very elaborative, so you can catch up very easily. Not all anyway. So what should you do so that you can have better grasping?
We, uh,
I know it is a difficult questions, but still I asked it, sir.
so how can I first? Also, you can follow according syllabus in internet. Some videos are available. You can learn from them. Freely available videos on different topics.
सर आपका कोई वीडियो है क्लासिकल का?
नहीं नहीं, मेरा कोई वीडियो नहीं है.
एक्चुअली होता है कि सर इसमें यूट्यूब में बहुत सारा वीडियो है, बट व्हाट इज ऑथेंटिक
Actually,
एंड
another question is maybe not all videos are not, they're not telling exact things, or
हाँ,
they are they are using their own assumptions that may not be true. That's true.
दैट्स द
But
प्रॉब्लम.
yeah, yeah. There are also established material. So the book is always better from everything else. You can read any book. Anything else?
Nothing, sir.
So can I quit?
Okay, thank you, sir. Thank you so much, sir.
Okay. Okay.
Sir, when
Thank
we
you.
will be
What is the action?
sir, when we will be having you again?
Mine?
Your next class, sir?
Tomorrow 4 p.m.
Okay, sir. Thank you, sir.
Thank you. Thank you, Anna.
And please do
Thank you, sir.
post your
Yeah.
Thank you,
PDF
sir.
into the
Yeah,
official
yeah, yeah.
email.
Yeah, yeah.
WhatsApp group.
Yeah.
WhatsApp group.
Yeah.
Thank you, sir.